Hello everyone. Today I'll present our work on a confirmation bias due to approximate active inference. Researchers study evidence integration in the context of perceptual decision-making tasks. For most of these tasks, a series of stimuli are presented one after another, after which subjects make a choice. Let's look at one such example. Here, a subject passively views a series of textures either oriented plus 45 degrees or minus 45 degrees. And at the end of the trial, the subject has to report which orientation is the majority. Now, we can compute how much weight was given to each piece of evidence over time in decision making. Interestingly, it has been shown in previous studies that sometimes participants' decisions are influenced more by early evidence, also called primacy or perceptual confirmation bias. Sometimes participants weigh each piece of evidence equally or optimally, and sometimes they weigh later evidence more, also known as recency effect. In a previous work, we have shown that approximate inference in a hierarchical model in which expectations influence our sensory inferences can explain such biases. Note that the example task I presented and evidence integration in general has mostly been studied in the context of passively presented evidence. However, the more common situation in the real world is where observers collect new information by performing actions. So one can imagine biases may also arise in the way new information is collected by performing actions. Here, we investigate how humans seek new evidence in decision-making tasks and if such active sensing also suffers from biases. Eye movements have previously been found to be optimal in detection and discrimination tasks. And the specific question we address is, are saccades to peripheral stimuli biased by existing beliefs about the correct category? We build on work showing that humans make goal-driven eye movements so as to maximize information about the correct category. Let me now elaborate the novel task that we designed to examine the mechanisms of seeking new evidence through eye movements in humans. Note that it would be extremely difficult to analyze entirely unconstrained behavior such as free viewing in the real world. Therefore, we designed a gaze-contingent task. This allowed us to have precise information about what information was available to the observer at any one point in time. In this task, each trial started with a fixation marker shown as a white cross on a gray screen, and the subject held fixation for 200 milliseconds. After 200 milliseconds, three oriented stimuli appeared on the screen. One stimulus around the fixation marker, plus two stimuli equidistant from fixation and each other. After 250 milliseconds, the stimulus at the fixation point disappeared, providing a cue to the participant to make a saccade to one of the two stimuli in the periphery. While the saccade was in progress, the non-chosen peripheral stimulus disappeared and two new stimuli appeared, now peripheral with respect to the new fixation point. After 250 milliseconds, the fixated stimulus disappeared again and the participant had to make another saccade to one of the two peripheral stimuli. This continued for 3 saccades. After a total of 3 saccades, participants reported their belief about the correct stimulus category for the entire trial. The orientation of each of the 9 stimuli shown in a trial was drawn from the correct orientation category with a probability of 0.7. This value was chosen to encourage evidence accumulation. Also, we explicitly instructed subjects to pay attention to all the stimuli and base their final decision on all stimuli, including those in the periphery. After each choice, an auditory feedback was provided to the participants on whether their choice was correct. It is crucial to mention that we chose the stimulus parameters and eccentricities in order to make the orientation of a foveated stimulus unambiguous for the participant, while providing some but not perfect information about the orientation of the stimuli in the periphery. If the information provided in the periphery is too low, then the brain will not be able to use it to decide where to move the eyes. If it is too high, then no new information is gained from moving the eyes. Next, we ran human subjects on this task and collected data from 8 naive subjects and 2 authors. On the right, Now, I am showing you the performance of the 10 subjects indicated by yellow bars, and the y-axis shows the percentage of correct responses. The bars with red borders indicate the two authors. We found that the participants could indeed successfully perform this challenging task. On average, the performance of the participants were consistently within 0.7 and 0.9, which are the threshold and perfect performance levels for this task respectively. This indicates that observers combined evidence across stimuli and were in the threshold regime. For each trial, we have 4 foveated stimuli shown with black borders and 5 non-foveated stimuli shown with magenta borders. Note that the non-foveated stimuli are presented at lower contrast to illustrate that peripheral information is impoverished as compared to the foveal information. Now, we can compute the temporal weights given to each of these foveated and non-foveated stimuli in making the final choice. We therefore used logistic regression to find the temporal weights given to foveated and non-foveated stimuli across all trials for each subject. Here, on the right, I am now showing you the logistic regression based weights of the 10 participants. The x-axis denotes the fixation number, and the weights are shown on the y-axis. Black indicate weights on foveated stimuli, and magenta indicate weights on non-foveated peripheral stimuli. Dashed black lines denote the two authors. We found that the black foveated weights are larger than those on the non-foveated ones. This shows that the observers weighed foveated stimuli more in the final decision, presumably because they were more certain about their orientation. Our task design also allows us to measure how a participant combined their current belief about the correct task category with the information they expect in the periphery when determining where to move their eyes next. In other words, we can test whether a participant used their current belief to make eye movements towards confirmatory stimulus in the periphery, leading to a confirmation bias or not. For this analysis, we focused on the subset of saccades for which the two peripheral stimuli actually had different orientations. We then used each observer's regression weights to compute an estimate of the observer's internal belief before making a saccade. We then computed the fraction of saccades that were made to a stimulus that agreed with the current belief as opposed to a stimulus whose orientation disagreed with the current belief. We now show the results of this analysis on subject data on the right. The probability of saccading to confirmatory evidence is shown on the y-axis, and again each yellow bar denotes one participant. We found that 9 out of 10 participants have a mean above 0.5, where 0.5 indicates random saccade shown by a black horizontal line. This analysis suggests that for humans, the integrated information from already fixated stimuli drives eye movements towards confirmatory evidence in the periphery. Let's try to model this task. First, let's try to understand how a Bayesian observer would decide to make saccades in such a task. Under natural conditions, the number of saccades isn't known in advance, so it's most likely that the brain will employ a greedy strategy that maximizes the information gain achieved by every single saccade. So, for a fixated location, the Bayesian ideal observer would compute the BAS score for each peripheral location and choose to saccade to the location with a greater score. However, we know that exact inference is intractable, so the brain necessarily performs approximate inference to compute the BAS score. Now, let's take a look at the BAS score for a location. Mathematically, BAS score is the mutual information between the category of the trial and the category at the peripheral location. The score has two components, one of which we call the sensory component and the other the cognitive component. We model the approximate inference during computation of BAS score by evaluating each term using samples. While neural sampling has been proposed, we simply use number of samples as a way to parameterize the degree of approximation. and we found that the degree of sampling-based approximation of each of these two components will determine the type and amount of bias in Saccard selection. If the computation of the first term is more precise than the computation of the second term, we see a confirmation bias. If, on the other hand, the computation of the second term is exact as compared to the first term, then we find anti-confirmatory bias, where evidence opposing one's belief are Saccarded to. Ideally, we would like to quantitatively fit our model to individual choices of each observer, but this turns out to be hard and extremely slow, and as an approximation, we made model predictions for the two summary statistics from the empirical data. That is, the accuracy and the probability of confirmatory Saccard for different values of model parameters. We simulated performance of varying sensory uncertainty, denoted as peripheral uncertainty on the x-axis, and in the y-axis we show the degree of approximation of the two components in the BA score. We represent that as a ratio of the number of samples used for cognitive component computation, denoted by n cognitive, to the number of samples used for sensory component computation, denoted by n sensory. The color indicates accuracy, with white meaning higher accuracy. We found that accuracy did not change much for changes in values along the y-axis. However, it did change for changes in values along the x-axis. This indicates that for our discrimination task, performance depended mostly on the sensory uncertainty and only very weakly on the degree of approximation used to compute the BA score. The isocontrol lines show values obtained from two example participants, and the dashed lines indicate 1 sigma error bars. Now, plotting the bias for the same parameter space, we now have the color denoting the bias here on the plot in the right. We found that as long as the sensory noise in the periphery was not too large, the strength of the bias depended primarily on the degree of approximation, especially of the cognitive computation as quantified by n cognitive. The coarser the approximation, the larger the bias. Furthermore, the bias ranged from 0.5 to about 0.8, covering the range of empirically observed values. The isocontrol lines show the same participants from the figure on the left. And note that when the sensory noise in the periphery was too large, that is towards the rightmost side along the x-axis, the bias disappeared due to the fact that regardless of approximation, the model could not infer any information to influence its Saccard. Now, since a coarse approximation of the cognitive computation as compared to the sensory component qualitatively predicts bias in the range that we observed in our empirical data, we try to speculate how that might be possible in the brain. Coming back to the BA score, the first component is the total entropy, and so we speculate that this local information computation is presumably carried out in local cortical areas, such as V1. And this has been previously modeled as a high throughput buffer which has fine representation of local features. So this is analogous to drawing more samples in our approximation of the first or sensory component. However, the second component is the noise entropy, which involves inferring the category of the trial and hence requires global information. So we assume that this computation is done in higher cortical areas of the brain where the representation is coarser. This would then be analogous to drawing fewer samples in our approximation of the second or cognitive component. Okay, now to summarize, we investigate whether eye movements are biased when sampling new information in a perceptual decision-making task. We test in a task where participants have to infer the dominant orientation in a gaze-contingent stimulus display. Our empirical results show that the accumulated belief about the trial category drives eye movements to locations that are confirmatory to the existing belief. Finally, the pattern of subject responses can be explained by an approximate inference model of information maximization. With that, thank you all for your attention, and here are the acknowledgements.